We know that Gibbs free energy can be calculated using the equation of delta G is equal to delta H minus T delta S. And if you know your enthalpy, your temperature, and your entropy value, you can therefore calculate delta G. Well, what is the relationship of Gibbs free energy at equilibrium? That's something that we can definitely relate. Delta G at equilibrium is actually 0. Therefore, what can a delta G of 0 at equilibrium tell us about K? Because we're always interested in K at equilibrium. Well, if we plug it into an equation that relates delta G, which is, of course, Gibbs free energy, to the standard free energy value of delta G naught, then we can relate that to, of course, K. So if we know that delta G is 0 at equilibrium, we plug in 0 for delta G, and 0 would equal delta G naught plus RT ln K. If we rearrange, of course, so that it doesn't equal 0 and we're solving for delta G naught, we'll move delta G naught to the other side. There's delta G naught, and that equals negative RT ln of K. So delta G naught equals negative RT ln K is how we can express G values or free energy to equilibrium constant, where of course your G is your free energy under standard conditions, R is your gas constant. This is the 8.314 joule per degree Kelvin mole value, so please note the joules unit, and of course ln of K is the natural log of your equilibrium constant. Temperature should always, of course, be in units of Kelvin as well. So all of your units should match the units of your gas constant, joules, Kelvin, and mole. The relationship between K and delta G naught is really what we are interested in determining. For example, which of the side of equilibrium is favored, the reactants or the products? Or are they favored equally? So by knowing something about delta G and K, that will be able to tell us a little something about what's happening at equilibrium. So here's a table that explains the relationship where if your K is equal to 1, you are actually going to be at equilibrium. That's something that's learned very early on in kinetics. If you take the natural log, or the ln of K as the equation states, the ln of 1 is 0. And when ln of K is 0, 0 times RT is 0, and negative delta G naught is also 0. So when delta G is 0, that is equivalent to K being equal to 1, which is the equivalent of being at equilibrium and your products and reactants being equally favored. If your K is greater than 1, let's say 2, hypothetically, the natural log of a number greater than 1 is a positive value. So let's say ln of 2 is 0.0 or 0.693. That's a positive value. And when ln of K is a plus, plus times a minus gives you a minus delta G. And negative delta G corresponds to a K value that's greater than 1, where products are favored over reactants. If your K is less than 1, so any fractional or negative value, in which case we don't really have negative values, so this would be a fraction. A fraction for K, when you have any number less than 1 and you take the natural log of it, the natural log, of course, the ln will be negative. So ln K, if plugged into here, the negative times a negative would make a positive delta G value. So positive delta G corresponds to a K value of greater than 1, in which case the reactants are favored over the products. So that being said, we're going to be able to relate K to delta G naught to what is happening at equilibrium using this table. You don't have to memorize it, simply know what a K of 1, greater than 1, and less than to 1 related to back in kinetics, and that will tell you what is being favored at equilibrium. By picking a hypothetical value, k of 1 of course is 1, the ln of 1 is 0, plugging in 0 will give you a delta G of 0. But for a k of greater than 1, selecting any number above 1 and plugging it in to your calculator will tell you that you're going to end up with an ln of k that is a positive value. Plugging in a positive value up here into this equation, a positive times a negative in the equation will of course give you a negative delta G. Whereas if you have a k less than 1 and you select a number less than 1, like 0.5, plug that into the calculator and take the natural log, the ln, you will get a negative value. Negative plugged into this equation times a negative will yield a positive delta G, in which case you know your reactants are favored over your products. So very simple, just looking at values and plugging them in. No need to really memorize. That being said, let's take a look at an example where we're going to calculate K. So it asks us to calculate the K value for the following reaction and determine if the reaction is at equilibrium. And if not, are the products or reactants favored? So which of those will be favored? So let's take a look. We're given this table of values, and from that we're going to then use our equation where delta G naught equals negative RT ln of K. So what we need is our delta G value, R, T, and we'll solve for K. So we know that R is a constant. Temperature, we're going to assume we are at 25 degrees Celsius, which is equal to 298 Kelvin. And you should be provided a value here. So I'm saying that we're at 25 Celsius, and we know that that's 298 Kelvin. But always watch for your temperature there. Delta G, we're given the G values, and here this is a table that gives you your G values, H values, S values. This is very much what an appendices might look like, or a reference table. This was the same table that we used for the Gibbs free energy calculation problem in a separate video, which is why you have all your values here. But in this case, we're only looking for G values. So we need to find delta G first and foremost, which is why we have this table. And this table we used in a previous Gibbs free energy equation, which needed H and S. So we don't really need any of those, but we just need G. We have 1 mole of each, so 1 mole times 1128.8 negative is the same. 1 mole of calcium oxide is negative 604.2, and 1 times negative 394.4 is 1. So again, we'd always have to multiply that by the number of moles because these values are all per 1 mole. But luckily, it is 1 mole for each reactant and product, and we don't have to worry about it. Just pluck those numbers out of the table and use them as is. So delta G, the change is the sum of our products G values minus the sum of our reactant G values. All right, and the sum of the products, which happen to be this number and this number, are going to be negative 394.4 plus negative 604.2 minus the sum of our reactants, only one reactant, that's negative 1128.8. So delta G is equal to negative 394.4 plus negative 604.2, simplified is negative 998.6 minus, of course, 1128.8, which is negative, and then a negative makes a positive, so negative 998.6 plus 1128.8 gives us a delta G naught value of 130.2 kilojoules. Alright, now we know what we can plug into here. Alright, so now we can go back and plug into our equation. Delta G naught equals negative RT ln of K. Delta G naught we just found is 130.2. That is in kilojoules. And then we have negative R, which is 8.314 joules per mole Kelvin, times T, which is 298 Kelvin, and ln of K. Notice how this is kilojoules and this is joules, so we need to make them the same. It's just easy enough to make this 130,200 by multiplying by 1,000, making that a joule. We're going to get rid of the units anyway, but we still need to make sure the units match, and it's just easier to multiply by 1,000 on that side and make it joules. So the joules and joules cancel out there. Moles we've accounted for since we all had 1 mole, and then Kelvin and Kelvin eliminate one another. So there's our R value. So delta G naught equals R T and ln of K. All right, let's just start simplifying. So 130,200 divided by negative 8.314 times 298 is really what we're going for. So the value for that is negative 2477.6 when you multiply these two guys, ln K. So 130,200 divided by negative 2477.6 should give you ln of K. And what do we get? When we divide that, we get negative 52.55 equals ln of K. And to find then K, we take the inverse log. That will give us K. And on this side, take the inverse log, makes that e to the power of negative 52.55. Therefore, K is equal to 1.5. 1 times 10 to the negative 23. So, that is the value for K that we were asked. We were also asked, is this reaction at equilibrium? And the answer is a resounding no, because K should be equal to 1 at equilibrium. So, the second part of the question was that if it's not at equilibrium, then what is favored? The reactants or the products? This K is significantly less than 1. And a K that is less than 1 will always favor the reactants. That also means that our delta G value should be a positive value. Let's check and see if that's the case. Our delta G value was indeed a positive value. A positive delta G gave us this value here that was negative, a negative ln K, which gave us a K that was significantly less than 1. All that should match our table. Negative ln K, a K of less than 1, a positive delta G. Yes, our reactants are indeed favored. So by just looking at the numbers, you can determine the table and confirm all of your findings. Positive delta G naught, a negative value for your ln of K, which gave you a positive value for K that was less than 1, favoring your reactant.